This video lecture goes along with the Week 10 lab on acid-base titrations and the hydrolysis of salts. So in lab, you were to have one student perform a strong acid, strong base titration and produce a titration curve based on that titration. Titration curve is a plot of pH versus either equivalence of acid added or equivalence of base added. In this case, we're adding hydroxide, so we're adding base. So the x-axis is volume of hydroxide added. And the strong acid that you were working with in lab is HCl, the strong base, NaOH. And so starting at a very low pH for HCl, what you would notice is that H plus remains to be the major species present, and so the species that's dictating the pH for a while, even as we're adding hydroxide. And then at some point we reach neutralization, and you see a sharp, sudden increase in the pH, and then it tails off at a much higher pH, and that is the pH correlating with the hydroxide concentration of the sodium hydroxide that has now overwhelmed the system. So we start out with mostly H plus, end up with mostly OH minus, and somewhere right in between these 2 points, we've got the equivalence point, and that is where the equivalence point is where the moles of H plus equals the moles of OH minus. So we don't have any excess H plus or OH minus. They have completely reacted with each other. And so the major species present here at the neutralization point is going to be the salt. So major species present is the salt that is generated from this chemical reaction. So we have to think about that balanced chemical reaction. In titration A1 for strong acid, strong base, we have HCl reacting with NaOH to give rise to a salt and water. So H2O forms plus the salt is NaCl. And so this is the major species present that is determining the pH. Determines the pH at equivalence point. Right? Because these two reactants equal each other, they cancel each other out at the equivalence point. All of the HCl has reacted with all of the NaOH, okay? Leaving only NaCl to determine the pH, and NaCl consists of Na plus and Cl minus. So we want to know if this is acidic, basic, or neutral. We think about the hydrolysis, okay, of this salt. So react in turn each ion with water and see what you get. If you get something strong, like sodium hydroxide, then we reason that this is not going to happen. Strong species don't form, they completely dissociate, and so we're really just left with sodium ions that don't generate hydroxide or hydronium, and therefore are neutral. Same thing with chloride ions. So a chloride reacts with water in hydrolysis to give rise to HCl plus OH minus theoretically, but HCl is strong, completely ionizes. This species does not form. And we're just left with chloride ions in solution, which, since they do not generate any equivalence of hydroxide or hydronium, is a neutral ion. Okay, and so for that reason, NaCl is a neutral salt, and the pH at the equivalence point of a strong acid, strong base titration is always going to be a pH of 7. Let's compare that to the titration of a weak acid, strong base, right? So our x-axis is still equivalence of hydroxide added, or volume added, and y-axis is still increasing pH. One difference is that we're starting out at a higher pH, okay, because this is a weak acid. This weak acid is CH3COOH, or acetic acid. The base is still sodium hydroxide. And so we're going to notice a more gradual increase in hydroxide, very gradual increase, and we're going to see the titration curve tail off at the same pH that we tailed off at before, because the major species present dictating the pH is the hydroxide ion, same hydroxide ion that was dictating the end of the titration curve in A1. So if we want to know, okay, this part of the very beginning of the titration curve is mostly H plus present dictating the pH, the end is mostly OH minus. What species at the equivalence point is dictating the pH? Okay, again, the moles of H plus equals the moles of OH minus. So the major species present is going to be the salt, which would be what? For the reaction of CH3CO2H plus NaOH, okay, we would generate water and a salt. And the salt that we generate is sodium acetate, NaCH3CO2. And so we're really asking, is this salt acidic, basic, or neutral? So we would determine that pH the same way we did. This is the compound that determines the pH at the equivalence point. It's the salt. And we would decide whether it's acidic, basic, or neutral the same way we did the other salt. We had already decided that Na plus is a neutral. And so it's acetate that is going to decide whether this salt is acidic, basic, or neutral. You notice it's an anion, which is a red flag for basic. So we're expecting this ion to either be neutral or basic. It very likely generates hydroxide in solutions. So let's just see. When we hydrolyze it, we get CH3CO2H, acetic acid. We know that's a weak acid because we know it's not a strong acid. Strong acids we memorized. Okay, and the other species is hydroxide. And so since it's weak, therefore it will form, this will form too, and hydroxide is generated. Therefore, this ion is basic. Okay, the CH3CO2 minus acetate is basic. Okay, so the entire salt is basic then, since the sodium component is neutral. So this species is basic, and right here we're going to see that the pH at the equivalence point is going to be greater than 7, because CH3CO2 minus is a basic ion, and sodium acetate is a basic salt. So those are the key differences between the two titration curves. And the rest of the lab was pretty straightforward, measuring the pH of common solutions. It's the hydrolysis of salts that is the major concept here, and whether or not those salts are acidic, basic, or neutral. And so we have a couple more of examples here. Let's say that the salt in question is potassium nitrate. Is it acidic, basic, or neutral? And if you don't want to write out the entire equation, you know, of K plus H2O, giving rise to its products of KOH plus H plus, then what you could do instead is a quick shortcut and react the water as HOH, crisscross the positively charged species with the OH of water and the negatively charged species of the H with water and see what you get. So this is a shorthand little way to determine what you would form upon hydrolysis, and then you could decide whether these species are strong or weak. HNO3 was memorized as a strong acid, therefore it doesn't form, and the ion that it came from is neutral. And KOH is a strong base. We would have to know that, and therefore the ion it came from is neutral. Okay, so if I was going to use that shortcut again for one more example, I could do this one. Okay, I'm going to use exactly the same method that I used above, our quick shortcut method, showing what products you get upon hydrolysis. Okay, and so we would get HClO4 as one product, and then we would get an aluminum species. Remember that small metals with large charge. So you might have predicted something like AlOH3, right? But you want to look at that as Al3+. Aluminum 3+ is an acidic ion. It's a small ion with high charge, okay? And this guy was strong, a strong acid, and so doesn't form. This is a neutral ion, and the aluminum part is acidic, we said. Therefore, the salt is overall acidic. Okay? And that's about